I'm Edgar Bermudez, a research associate at the Canadian Centre for Behavioral Neuroscience in the University of Lethbridge in Canada. In this talk, I propose that spatial navigation is a great area of interest for neuroscience and AI to converge and help each other in the understanding of cognitive processes. This talk is based on a recently published paper. Here, I highlight how neuroscience research in this area can benefit AI. However, if you want to know more about how neuroscience can also benefit from AI approaches to study the brain, you can check out the full paper. Arguably, being able to move and direct sensors and actuators gave an important evolutionary advantage in early organisms. Therefore, this is an important capability that is worth devoting resources to. For an agent that navigates in space, it is necessary to keep track of the orientation of the body and the distance traveled. With this information, biological agents can build a spatial representation of the world. A large proportion of what we know about how the brain processes information to navigate, at least in mammals, come from research in rodents. The main areas of the brain that are involved in processing spatial representations to solve spatial navigation are the hippocampus and the entorhinal cortex. However, there are more structures that also compute spatial features. For the sake of time, I will not describe the neuroscience in detail. You can find more about that in the paper. There are several reasons to propose spatial navigation as a great area from which AI can benefit. First, there are multiple areas in AI that deal with the key concepts that are directly or indirectly involved in spatial navigation, in addition to the more obvious examples like autonomous robots and driverless cars, such as learning and memory. These concepts are very active areas in AI, especially in artificial neural networks. Second, since this is an extensively studied area in neuroscience, there is a vast amount of experimental brain and behavioral data that can be used to develop AI models and test theories in the areas that I mentioned. Due to the embodiments and situatiness of the task, there are explicit biological restrictions that can be used to guide the development of AI models such that the solutions proposed can be directly compared to experimental data. One reason to propose this area that I find particularly interesting is the relationship of spatial representation in different reference frames with learning and memory. I think that understanding how these processes are implemented in the brain can be of great benefit in AI. Following these ideas, it has been proposed that the transformation of spatial information from an egocentric frame of reference to an allocentric one could be also used to extract semantic knowledge from repeated exposure to episodes. Therefore, the transformation of these reference systems could be used in artificial agents to make them more adaptive and to learn to generalize quickly. Recently, there have been important developments in how AI can be used to study these processes using deep reinforcement learning. In these approaches, spatial representations emerge from biologically relevant restrictions that make it easier to validate artificial and neuroscience experimental data. In summary, studying how spatial navigation is implemented in the brain can greatly benefit AI. The intersection of AI and neuroscience research in this area can bring exciting breakthroughs in the near future. Finally, I want to acknowledge my co-authors Ben Clark at the University of New Mexico and Harold Wilber at Florida State University. Thank you very much.